All right, so in this first problem, we just need to identify whether each of the following describes a discrete or a continuous random variable. And what we're really boiling down to are the types of numbers we would get something that are set and countable, where you can't split them any further past a certain point, or are they numbers you could continue to like split down further and further and have smaller and smaller or more and more decimal places, something like that. So the time it takes a cross-country runner to complete a race, time in general, you can continue to split down to fractions of a second. In real life, the only limitation is your stopwatch, but we could always get a more and more accurate device to measure that time. So that one is going to be continuous. B, the t-shirt sizes sold at a souvenir stand in a day. Well, when you're talking about t-shirt sizes, there are set sizes. In some places, a little more than other, but you're going to have some sort of maybe an extra small, medium, large, extra large, maybe even larger than that. But they are set and finite and countable. There's only certain sizes. You can't break down and have like a large 0.67. So this one would be discrete. You can't split down between two sizes any further. C, the heights of players on a football team. Now, on the one hand, I know that usually on a roster, you would, if you're listing this, you would just go to like the nearest inch. But height in general as a measurement can be split further and further down if you get a more and more accurate measuring tool. So not talking about necessarily what's listed on the roster, but the actual heights of something would be continuous. Next, the diameter of cedar trees being harvested for lumber. So if you're measuring the diameter, again, when you're talking about any sort of measurement is generally going to be continuous because it's only limited by the measurement tool. With a more accurate tool, we could split between or split down our measurements to smaller and smaller decimal places. E, the number of home runs hit by each player on a baseball team. Well, in this case, we are counting something. And if you are counting something, again, you can't have 4.5 home runs or 4.38 home runs. So this one would be discrete. Pretty much anytime you're just counting something. F, the number of episodes of a TV show watched on a streaming service in a day. Well, there might be a large range of numbers on any given day. Some days way more, some days way less. But you're still talking about counting how many episodes. And yes, I know in real life you can watch part of an episode. But when you're taking demographics or when you're looking at the number of episodes watched, they're counting. They're not necessarily looking at like the measurement of how many hours, at least based on this. So this one would be discrete. And then last one, the weight of bags of apples picked at an orchard. Well, when you're talking about weight again is kind of a measurement. You could split further and further if you have a more accurate scale. And I've seen some scales that go like down to the fraction of a fraction of a fraction of a pound or a gram or whatever. So this one is continuous. All right, so let's take a look at number 2. If the data below gives the number of hours a sample of high school students spend per week on their homework. If Shayna spends 6 hours on her homework each week, what is her percentile? Well, so we want to know basically how many values are there at or below 6. So we need to count up all of those, which would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So there are 22 that are at or below 6 out of 23, 24, 25, 26. And then if we divide, we end up with 0.846. So that would be the 84.6th percentile. The only real difference with number 3 is, so in that one, we actually had several scores right at the score we were interested in. In number 3, we want to know the percentile for a player who is at 5'3", which is right here, but we still want everything at or below. So we need to count up all those dots, which would be 1, 2, 3, 4, 5, 6, 7. And then altogether, there are 8, 9, 10, 11, 12, 13, 14, 15. So we're really looking at 17 divided by 15, which is 0.467, or the 46.7th percentile. All right, for the next problem here, we need to make a dot plot from this data. So the first thing that I would do is sort this data on your calculator. So I'm going to jump over to the calculator to do that. Just to making our dot plot a little bit easier, it'll help us know how far we need to make our number line. So first go in, if you have any data in here, if you hit clear here, nothing's going to happen. But if we go up to L1 and hit clear and then hit enter, it'll clear the list out. And then you can go in and you can type your list. I am going to skip ahead in the video. You don't need to see me typing in these numbers. And then once all your numbers are in there, then we can sort them. So go to a blank screen, hit stat. I'm going to sort in ascending order. And then I just need to tell the calculator to sort list 1. And then hit enter. Now I know my number line needs to start at 6 and go up to 17. And I can just scroll down my calculator as I make my dots to make sure I don't miss anything. So I know my number line now needs to go from 6 up to 17, so I would draw that in. When you're doing number lines for a dot plot, you wouldn't have to mark every number. You could do just like the evens. Here it's not so many numbers, so I think I will draw them. So here's 6, 7, 8, 9, and 17. So now we just need to go kind of scroll down our list and make our dots as we go. And I can't have the calculator right next to me on the same screen just because of the way technology works. But I should have 2 dots at 6, 1 at 7. Then I jump to 10, 11. I've got 2 12s. I've got 2 13s. I've got 2 14s. Now, I did not do a very good job ahead of time counting to see how big I should make my dots or how much room I have. And I've got, let's see, 1, 2, 3, 4 15s in my list. So this was not, a very well planned out. One thing I almost was going to do that's really not great with a dot plot, we really should try and keep them evenly spaced. Simply because otherwise, we would want to know where like the tall stacks of dots are, and if you squish some together and others are spaced out, it can be misleading. But anyway, we have 4 6s again, and then I've got a 17. So what I should have done that might have been better is ahead of time figure out how many of each number I have just by like counting and see what my biggest stack of dot is and make sure I leave enough room for all those dots. Otherwise, if one of these had been like 8 dots, had a way big graph down here, and then I might be forced to try and scramble to fit them in. So I survived this time. It did okay, but it's probably better to plan your size a little better than I did there. So for the split stem plot, we want to sort again. So I'm going to hop over to the calculator and do some sorting. Make a split stem plot. So we need to know how far we need to go down and how far up we need to go for our stems. So again, I'm going to go into my list, highlight L1 and hit clear, and then hit enter. And then you can start typing in your numbers. Just like last time, I'm going to jump ahead because you don't need to see me type a bunch of numbers. And then once I have this here, I'm going to clear out our second mode. I want to sort in ascending order, and I'm sorting list 1. So now I need to have a stem that goes at least down into the teens. And I need to go all the way up and have both 6s for the lower 60s and the upper 60s. For my stems in the teens, I really don't need both 1s. I only have numbers that are 15 or above. If you put them both, that's fine. In the middle, though, we need to include 2 2s, we need to include 2 3s, 2 4s, 2 5s, and 2 6s. You can't skip any stems in the middle, even if you don't necessarily need them for specific numbers. So I did not leave a ton of space for this one. Sorry about that. It was not intended to be that way to make life difficult. But I know from sorting I need to have, really need 1 1 for the upper teens. But then I need 2 2s, 2 3s, 2 4s, 2 5s, and 2 6s because I have numbers that go all the way from the upper teens to the upper 60s. But again, kind of like the dot plot, once you have it sorted, and you don't technically have to sort it, I just think it makes life easier. I don't like that line. It's a little better. So then I'm just kind of scrolling down my list. In the high teens, I need an 8 and a 9. In the lower 20s, I have a 0 and a 2. Then I only have a 7 in the upper 20s. In the lower 30s, I've got a 31. In the upper 30s, I've got 3 5s. Kind of like I mentioned with the dot plot, we'd like to try and space these pretty close to evenly so that if there's 3 digits, it looks more than 2 digits and it kind of matches up okay. But it doesn't need to be perfect necessarily. So now I've got a little bit more in the lower 40s. I have a 0 and 3 2s. Then I keep scrolling. In the upper 40s, I have 45, 48, and another 48. In the lower 50s, I have a 51, a 53, and a 53. I have nothing in the upper 50s, but I can't skip that upper 5. I still need to have that there because now that we want to be able to see that, oh, there was a gap in the upper 50s. In the lower 60s, I have a 60, a 62, and a 63. And then I have a 67. So that would be my split stem plot. I'm almost done. I'm not quite finished. Hopefully you're thinking, or maybe even already included the thing you need, which is a key. And it doesn't matter if it's a real number. I could say that 3, then my line, then 2 equals 32. 32 isn't a number on my list, but I can still use that as my example. We just need an example for a key. And that's our split stem plot. All right, and for the last one, we're looking at our cumulative relative frequency graph. And really, we're just doing some tracing over and down, or tracing up and over. This one's nice because they actually included some grid lines. Sometimes they don't. It's a little bit harder to tell exactly where things are at, like in my example in the original video notes. But as far as what is the center is the 50th percentile. So 50th percentile would be here. I would want to trace over till I hit the graph, trace down, and that score would be 25 grams. So the 25 grams is the 50th percentile, which is the center of the distribution. B, what percentile is a drink if it has 30 grams of sugar? So now I'm starting at 30 grams of sugar, tracing up until I hit the graph, tracing over. If you have 30 grams of sugar, you are at the 60th percentile. And then last but not least, how many grams of sugar does a drink at the 90th percentile have? So now I need to trace over. Here's where 90 would be, till I hit the graph, then trace down, and I'm at 45 grams. Now these ones are all nice and exact. You might have some that are a little bit more in between. Just estimate the best you can. Like if they ask for the 95th percentile or 93rd percentile, we might have to estimate, figure out that it's roughly in here or wherever it might be, and then trace down and just estimate the score and maybe say that it's like 46 or 47. But these ones are all really nice.